Morning. Hello, good morning, good evening, everybody, wherever you might be. It is today my great pleasure to introduce MATTHIAS SCHÖTZ. He is my postdoc here at IMPAN, and he will now introduce his research stuff to us. And it seems very interesting because these are Gelfand-Naimark theorems for ordered star algebras. MATTHIAS, the screen, the Zoom, the floor is yours. Take it away.
Thanks. Thanks for giving me the opportunity to give a talk here. Now, as you may see from the title, the idea of this talk is to present to you a way how to generalize the Gelfand-Naimark theorems from the setting of C-star algebras to the more general setting of ordered star algebra. So, to give you a small overview, I will of course give you the definition and many examples of ordered star algebras. Then I will talk about the bounded case, which is basically C-star algebras, pre-C-star algebras, and how this both can be dealt with in the setting of ordered star algebras. Then we go on to the representation theorems for a certain class of ordered star algebras, namely the sigma-bounded closed ones. And hopefully there's a little bit of time left in the end, so that I can give also some remarks about what the results mean for non-commutative geometry and for quantum physics, some philosophical marks.
I have a question. Are these algebras unital or not necessarily?
Yes. So I will only talk about unital star algebras, because having no unit is just too complicated.
And are they commutative or
no?
commutative?
They may be commutative or non-commutative.
Okay.
So in general, this will be about ordered star algebras, operator algebras, ordered vector spaces. Real algebraic geometry will play a role here. And also, I will give a comment on Archimedes and how this game is used in different mathematical communities.
Wait, so Archimedes was already involved in noncommutative geometry, right?
In a certain sense, apparently, because his name will
Good. I like it.
So, let's start. So the definition of a star algebra, I guess you know it. A star algebra for me is always a unital associative algebra and always over the field of complex numbers. And it's a algebra endowed with an antilinear involution star that fulfills this typical condition that AB star is B star times A star. And for star algebra, I will write AH for this set of Hermitian elements, Hermitian meaning an element A is its own conjugate. This is a real linear subspace of the whole star algebra. Oops. Okay. Star algebras are clear. What is an ordered star algebra? There we need the notion of a quadratic module on a star algebra. This is a subset, Q, always a subset of the Hermitian elements that fulfills these three axioms. So it's closed under addition. It's stable under this kind of conjugation, Q going to A star QA with an arbitrary star algebra element A, and it contains the unit. So think about a quadratic module as an abstraction of the set of positive elements in Farm's good notion of positivity. And an ordered star algebra is very similar to this. It's a star algebra with a partial order on the Hermitian elements that fulfills these three axioms that you have here. So if we start with two elements B and C, two Hermitian elements, such that B is less equal than C, then we may add a third Hermitian element D at both sides of the equation of the inequality. We may conjugate the inequality with an arbitrary star algebra element A, and we want the unit to be, positive. And then you see, we will write A plus H for this, just for the set of all the positive elements with respect to this order. And then it's not hard to check this set of positive elements that fulfills the conditions, the axioms of a quadratic module. And also, important condition, it fulfills this intersection property. So basically there's no element except the zero, which is both positive and negative, right? And conversely, so we can characterize an ordered star algebra also as a star algebra that has a quadratic module Q of positive elements that fulfills this intersection property. Basically, if we have such a quadratic module, we can construct an order by saying that A is less equal than B if and only if B minus A are in this quadratic module Q. Okay, so these are just two different ways how to look at the definition of an ordered star algebra, similar maybe to the setting of ordered vector spaces, which you can see as a vector space with an ordering, or as a vector space with a convex cone. And it just depends on the situation, which way to look at it is more convenient.
So this is about the positive cone.
Yes, so this quadratic module will always play the role of the cone of positive elements. Positive by definition, essentially.
Why is it called a module?
Yes.
Kind of confused.
Yes, this is, I mean, this notion of a quadratic module that's originated in real algebraic geometry, where everything is commutative. And then this means basically this second condition, that basically means that it is a set that you can multiply with quadratic elements. So it's a module for quadratic elements.
Okay.
And of course, in a quadratic setting, you have to generalize it to this condition and not multiply from the left per quadratic.
So it's a module over what? Over C?
Sorry?
It is being seen as a module over what?
No, it's not a module. Here is just a name.
It's the name.
Yeah. Although you could try to hook up maybe a tensor opposite, whatever, but it's
Just a name.
yeah.
Yes, but it is a module.
Over a tensor opposite, right?
Not exactly. It's a module over the subalgebra in A of tensor tensor A generated by elements of the form
AA star.
Yes.
Okay. Yeah. So you can justify the terminology if you wish to. Okay, but you're right. In the commutative setting is obvious.
Yeah. So
Thank you.
the reason is more. I think it's a historical reason.
In fact, it's a semi because it's a semi ring.
Okay.
It's a module over the semi ring generated by
Semi module.
over a semi ring.
Okay.
Okay, so the easiest example of an ordered star algebra is just an ordered star algebra of functions. So for any set, I write C to the X for the star algebra of complex valued functions on X. Star algebra with respect to the pointwise operations, pointwise addition, pointwise multiplication, pointwise complex conjugation as the sign evolution. And then, of course, the Hermitian elements are the real valued functions. And well, there's a standard way to order this. It's the pointwise order, right? A less equal than B if and only if A of X less equal to B of X for every point X. And this way, with this ordering, C to the X becomes an ordered star algebra, and the quadratic module of positive Hermitian elements that are the positive valued functions. And I should say here, for me, the adjective positive always means greater or equal 0. So I will not go through the pain and call things negative, just to indicate that the 0 is included. So positive means greater or equal 0. And another important example of star algebras or ordered star algebras of operators. So assume we have a pre-Hilbert space D with an inner product. Then I will write L star D for the star algebra of adjointable endomorphisms of D. So that means linear maps for which there exists this joint endomorphism A star that fulfills this usual condition. You can bring it to the other side of the inner product if we conjugate it. So here, adjointable, that's understood in a fully algebraic way. So that's not the way how we would construct the adjoint of an operator on a Hilbert space. And in this case, the Hermitian elements of the star algebra that are those endomorphisms for which this inner product C with HC is always real. That's standard argument. argument pipe. And this algebra becomes an ordered star algebra by defining A less equal than B if and only psi applied to A psi is always less equal than psi applied to B psi. And essentially, this is the usual order of operators on a Hilbert space. So the quadratic module of positive Hermitian elements in this example are the usual positive Hermitian operators. Those endomorphisms A for which the inner product psi with A psi is always greater equal to 0.
What about pre-Hilbert modules? So pre-Hilbert modules, if the scalar product takes values in some, let's say, star algebra, then you can speak about positive.
I
Would be an example of the general.
I think this will give you other examples. Yes.
Okay. Thank you.
Yes. And so you could define all-star algebras also alternatively as well using the language of operators in a Hilbert space. But that would be much more involved. Then we would have to start with a set of operators in a Hilbert space, which has a common dense domain, and the adjoint has to be such that its domain includes the domain you started with. So very complicated, but it can be done. But this way is just a quick and easy way to define all-star algebras.
Well, you can consider all the unbounded operators that is closed and densely defined that is affiliated with a fixed abelian von Neumann algebra. There will still be an example.
Oh, sorry, I didn't.
You can consider all the affiliated operators affiliated with a abelian von Neumann algebra to avoid this common domain definition thing. And still, it would be a very nice example.
Yeah, sounds maybe it sounds right. Yes. Thanks. So another example, pre-C star algebras or star algebras. So we'll try to have everyone on the same page. C star norm is a norm on a star algebra A that is submultiplicative and fulfills this C star condition. Norm of A star A is the norm of A squared. A pre-C star algebra is simply a star algebra with a C star norm, and a C star algebra is a pre-C star algebra that's complete as a norm vector space. And of course, there are the Gelfand-Naimark theorems for C star algebras that tell you every C star algebra is essentially a star algebra of operators. So, of course, C star algebras are examples. Of course, star algebras of operators are examples. But
would I ask you just a silly question? Because you say that this pre-C star algebra is by definition endowed already with a norm, C star norm, it means that in fact it is already a subalgebra of a C star algebra which you get after completion.
yes,
Okay. So it's not just a star algebra that you can then quotient and complete. It's already because it is a norm, so it kills all elements that would be like self-adjoining potents.
yes.
Okay. Otherwise, it would not be a norm. Okay.
And also, I have a remark, since in the literature one can find also another definition of a pre-C star algebra, and the additional assumption is that this algebra is complete with respect to some family of semi-norms, which is strictly which induces a topology which is stronger than the original norm topology. So this is another definition, which is, I presume, presumably not equivalent to this one.
It sounds like Frechet algebra to me, no?
That is called true C star.
Yes, it is Frechet, but also it is also endowed with this C star norm, and it is not complete with respect to the C star norm, but it is complete with respect to this family of semi-norms.
Okay.
And these conditions are to make the K-theory for such algebra is the same as the K-theory of the completion of it.
Are you talking about the so-called local C star algebra? Oh.
Maybe.
Maybe.
I think it should be called local system algebra in Blackada's book. What you say, yeah.
I know this this terminology from this book of Variri, Elements of Non-Commutative Geometry. It is how he calls this these algebras.
Okay.
As pre-system algebras.
So the main example would be, for instance, smooth functions.
Yes, exactly. Sure.
Yes.
Smooth.
Okay.
Okay. Yeah, I will. So the point I will talk about pre-system algebras is that some of the statements that I will make would be a little bit silly if I made them for C-star algebras, because C-star algebras are so nice. The norm is uniquely determined, and all the unitary star homomorphisms between C-star algebras are automatically continuous, and then some statements would just be silly because they would automatically be fulfilled. So that's the reason why I will talk about pre-C-star algebras in this sense, star algebra or C-star norm. Okay, and the nicest way to turn a C-star algebra or pre-C-star algebra into an ordered star algebra is by noting that there's a unique order on every C-star algebra that turns it into an ordered star algebra. And this order is, well, we can determine the order just by giving the positive elements. And the order is determined by the usual positive elements of a C-star algebra. And I will give you parts of the proof. So the one part, that's showing that this definition of A plus H that I gave here is actually a quadratic module that turns the star algebra into an ordered star algebra. Then you have to go through all these axioms, and this is actually quite hard if you know nothing about C-star algebras. There you have to go through all the Gelfand theory of Banach star algebras to actually show the things like the sum of elements in positive spectrum has again positive spectrum. So this is the part that is standard C-star algebra technique that I will not give you here. So that A plus H is a quadratic module and fulfills the section property that's standard but hard. The thing that I will prove to you is the converse statement. If we have a quadratic module fulfilling this intersection property, then this quadratic module is automatically just the standard quadratic module of usual positive elements in the C-star algebra. So start with the one inclusion. We have an element, a positive element in the C-star algebra. Then, because we can construct square roots, we can express A as B star times unit times B for some element B from the star algebra. And because the unit is in the quadratic module Q, and because of these axioms of quadratic modules, we see that A is also in Q. So this way around was easy. Other way around, we want to show the quadratic module Q is contained in the usual positive elements of the C-star algebra. So if we have an element of the quadratic module Q, we can always decompose it, because it's Hermitian by definition of quadratic modules. We can decompose it as A plus minus A minus, with being the positive and negative parts in the usual sense. Okay. So A plus and A minus are positive in a C-star algebraic sense, and their product is 0.
By the spectral theorem.
There you need continuous calculus spectral theorem. C-star algebra techniques. Now then you look at this product A minus times A times A minus. Because the product of A plus times A minus is 0, this is minus A minus to the third power. And because A was in the quadratic module by assumption, we find that minus A minus to the third power is in the quadratic module Q. On the other hand, A minus was positive, so A minus in the C-star algebra sense. So A minus to the third power is also positive in the C-star algebra sense. We have already shown that the C-star algebraic positive elements are in Q. So a minus to the third power is also q. But then, because q intersected with minus q is just a zero, we find a minus to the third power is zero. And therefore, well, using again some C-star algebra technique, a minus is zero, and this means that a was just the positive part, and therefore positive. Okay. So there's a unique way how we can turn any C-star algebra into an ordered star algebra. And there's a corollary, there's a canonical way to turn a pre-C-star algebra into an ordered star algebra by using the order of its C-star completion. But on pre-C-star algebras, this order would be generally not uniquely determined, it's only uniquely determined if you use the norm.
Sorry, by this, could you come back to the previous one?
Yes, it's right here. Yes.
Speaking about this order of the C-star completions, you mean the intersection of these positive elements in C-star completion with the algebra itself?
Yes.
Because it must be contained in the algebra.
Yes, of course.
So you pull back the quadratic model algebra to the your original pre-C-star. Yes. Ways how you can construct examples. More of an algebraic nature. So for any star algebra, we can construct this set denoted A plus plus H. They are called algebraically positive elements or sums of Hermitian squares. So a Hermitian square in a star algebra is an element of the form A star times A. So, well, by this definition, A plus plus H is the sum of the Hermitian squares. And what you can show is this cone of sums of Hermitian squares is the smallest quadratic module that you have on the star algebra A. And you can turn A into an ordered star algebra. So you find some compatible partial order on it, if and only if this quadratic module fulfills this intersection property. Okay, I think I can be a little bit faster here. So basically, we check that this is a quadratic module that's hard. It is also contained in every quadratic module that you put up. Easy to check. Conversely, if we have a star algebra that can be turned into an ordered star algebra, then these sums of Hermitian squares are inside the positive elements of the star algebra, and that means that they fulfill this intersection property. And the other way around, if they fulfill this intersection property, then we can define the order as the one that makes these sums of Hermitian squares positive.
So by convention, you allow an empty collection of such an star an, for which the sum is equal to 0.
Well, 0 is positive, right?
But the definition is from n from 1 to n.
You can just take A1 equals 0.
Like an
And
empty
it's
set
0,
of
0 star
sums.
0 is 0.
Oh, sorry.
You don't have to consider empty sums, but of course you can.
Sum over an empty set is 0.
Yeah.
Yeah,
You could,
but 0 star 0 is also 0. And 0 belongs to A.
No, you're right. Yes, you're right.
So in this definition, the 0 is included because it's you can use big N equals 1 and A1 equals 0.
Exactly. Yes.
Ah, so okay.
Yes.
Okay.
It's maybe not the most.
Yeah.
Okay, and well, I've given you the nice examples: star algebras, ordered star algebras of function, ordered star algebras of operators, C-star algebras. Now let's go to less nice examples. So we consider the unit circle S. And on the unit circle, the algebra of continuous complex valued functions. This is the pointwise addition and pointwise multiplication, but with an unusual star involution. So we define A star at a point Z to be the complex conjugate of A at a point minus Z. So in addition to complex conjugation, we also introduce this inversion. And you can check, this way you still get a star algebra, a commutative star algebra. But, well, then there's a very strange element in this star algebra, the identity. So meaning the function that maps every element set of the circle to itself, which is a complex value function, right? This is the problem. It has a property that its star times it is minus the unit. So because, well, at any point z, its star gives you minus z bar, and then you multiply this with z, you get -1. So -1 is a Hermitian square in this star algebra. This is a little bit weird. And from this it follows that every Hermitian element is a sum of Hermitian squares, because well, you have this decomposition here. So basically, the a square terms, they will cancel here, and the constant terms, they also cancel, and the a remains. So what does this mean? The sum of Hermitian squares are all the Hermitian elements, so this intersection property that's not fulfilled. That means this star algebra cannot be turned into an ordered star algebra. However, it can be turned into a Banach star algebra, meaning, well, basically a C-star algebra without the assumption that the norm fulfills the C-star property. The usual way. So the norm is the usual maximum norm on the circle.
You mean supreme?
Well, supreme, but it's also a maximum.
The circle is compact.
Because it's compact, yes, okay.
So what does this show? If we relax the assumptions of a C-star algebra in a topological way, just a little bit, we end up with Banach star algebras, and Banach star algebras can be very strange. But such strange star algebras cannot be turned into ordered star algebras. So this ordering, that's actually, that's already a very nice property, right?
Sorry, what about the example when a star of z by definition is a of z star or z bar, and the value also under the bar? Then it will be not pathological, I suppose.
No,
So,
it's just a convolution algebra of
This
the
is the
circle
same.
group.
But we are on the circle, so
Yeah,
okay, it's minus. It's not
No.
-1. It's
it's
minus.
not minus, minus
Okay.
the inverse.
Okay, I see.
So without this minus in here, we
I
just
think-
have very
yeah, but I'm asking about z inverse instead of minus z.
If you take a,
Or this will be not pathological, or is
if you take the inverse, it will be the
wow.
subalgebra of the convolution algebra of,
yeah, precisely.
right? So
Yeah, I'm asking about the convolution algebra.
then there's an obvious order. It's the Euro one. It's just a you
Yeah.
take it, the dual. It's Z, and yeah, it's C, a subalgebra of C of Z via the Fourier transform, of course.
So how to understand the difference between z inverse and minus z? You have two maps from S to S. One is the inverse, the second is this reflection. Okay, so why this is pathological and the other example is not pathological?
So I have to say, I don't understand the other example. So I don't exactly know whether it can be turned into an ordered.
If you put instead of minus z in this formula, z inverse or z bar, which is the same on the unit circle, you obtain the convolution algebra. Okay, and this is of course the star algebra with probably positive definite structure.
How do you know that this one does not have similar pathology?
Because we know this, we know at least this.
You have a faithful representation of it on L2 of S.
It's a convolution algebra,
Yeah,
which is star
it
algebra.
works with any group.
Yes, but you have a different norm. Yes, in this example, you have a
You
norm
don't care about the norm.
you
You just view it as algebra.
algebra.
Represent it as a phase plane, as a star
Problem is purely algebraic.
Yeah, exactly.
Yes, so for pure algebra, it's fine. Yes.
Yeah.
So the inverse is good. The reflection of the circle is wrong.
But could this example be completed to a C-star algebra, or it's
Yeah.
I think
Yes. convolutional algebra of Z.
Okay, then it should be really nice.
Actually, I think there's another way to construct such pathological example, which is slightly simpler. You just need the -1 to be positive, right? So you view C, the complex numbers, as a real algebra. So that -1 is indeed a square, it's I square. But this time you complex C as a real algebra. So you consider C, tensor C over the reals. And you equip it with the natural star involution on the second tensor factor. And this time you still get somehow this is the minimal pathological example because -1 should be positive now. And you get the same thing.
So in a way, I treat it as an answer to Tomek's question.
Yeah, exactly.
Why do you create such a pathology? To create such a pathology, a minimal requirement is to make -1 positive.
Exactly.
Yeah.
You can even take the Hamiltonians, quaternions, -1 is a square, and you complexify it.
Yeah, but my question was about the difference between Z inverse and -Z as a map from S to S. Is there some characterization of
Functions.
good and bad involutions on this topological space? One completing to positive structure and one which cannot be completed.
But I don't know how to give it an alternative.
But it's interesting.
No idea. Okay, so basically, start was in general can be pathological. Even banner star algebras can be pathological, but ordering excludes at least some pathologies. Another pathology that we cannot exclude just by demanding ordered star algebras is this here. So we take the unital subalgebra of this of the 2x2 complex matrices. So this is basically just a two-dimensional commutative subalgebra. But we don't use the usual star involution on it, but just the star involution that's given by complex conjugation of all the elements. This way we get a commutative star algebra. And then you can check the sums of Hermitian squares are those matrices A, B, 0, A, which either A is strictly greater than 0, and B is just any real number, or A and B are both 0. So basically, in order to see this, you just have to calculate the square of one such element. And then you will see on the diagonal, you get a square of a real number. So this has to be created equal 0, and the off diagonal, you can get basically everything.
So the difference with the sister algebraic case is consists in existence of this nilpotent.
Exactly. So in this
are contained in this A++.
This star algebra has a nilpotent Hermitian
nilpotency.
So, but because it's easy to check that these form of Hermitian squares, they fulfill this intersection condition.
Wait a minute, but this upper triangular matrix is not Hermitian. So what is the conjugation?
So
Element-wise complex.
Okay.
Yeah.
There is no transposition here.
Yeah. So each element is just real value such. And A plus plus H intersected with minus A plus plus H. Well, from this you see that's just 0. So this algebra can be turned into an ordered star algebra. However, there are nilpotent Hermitian elements which are not 0. Just take A0 and B arbitrary.
And they are Hermitian.
They are Hermitian. So we cannot exclude all pathologies.
But then you take B real, of course.
Yes, you take B real. But note that will become later. There are these elements epsilon, B0, epsilon, strictly greater than 0 epsilon and arbitrary real B. Well, maybe B under equals 0. This is positive. This is a sum of Hermitian squares. But if we go to the limit, epsilon going to 0, then this is no longer positive. So what happens in this case is that this, with this notion of positivity, we get a non-closed quadratic module. And this is basically the reason for the topologies here.
Wait, so here just epsilon needs to be positive, b can be negative, right?
Yes.
Epsilon tending to 0 plus.
So, and if, because I want to exclude such pathologies, because I want to go to find a representation theorem, I need another condition that I can put on my modest algebras. And this is the notion of a closed modest algebra. But I should say already, this is not a topological notion. It's more an order theoretic closure, or no order theoretic notion of being closed. So we say order algebra is closed if the following is true. If we have two Hermitian elements, A and B, such that A plus epsilon B is positive for every epsilon greater than 0. In this case, A is already positive. So think of it, if we have a line in this through the Hermitian elements of the star algebra. This line will intersect the positive elements somewhere at a line segment. The condition for A to be closed is that this line segment, this intersection of the line with the positive elements, that this is closed. So in some sense, it's a very weak notion of being closed only on these one-dimensional line segments. And we don't need a topology to.
So the only topology is along this direction of this B.
That's basically the vector topology on R. Topology, yes.
So if I understand correctly, this condition is equivalent to the requirement that strict convex combinations is positive, implies each of the elements is positive, right? If I use a strict convex combination, I know any strict convex combination of two elements is positive, and then each one of these elements should be positive.
I think it sounds equivalent.
It is equivalent to this one, right? I think.
Yes.
And you can use arbitrary finitely number of elements to do strict convex combination. It should, by induction, it should still be the same. Okay, never mind. It's just an observation. Yeah.
Yeah. Okay. Yeah. So maybe I should be a little bit faster. So the typical examples of these closed ordered star algebras, star algebras of functions, star algebras of operators, these star algebras. You see this quite for C to the X L star of D, you see this as an immediate consequence of the definition. C star algebras then is maybe known, so property that you have to prove, and of course for all the unit star functions. A non-example would be this example of this matrix example that we had before.
I have a question. If you have a vector space equipped with a non-degenerate quadratic form, then you can define a joint endomorphism, and you can use this to define your A++.
Yeah, I mean,
Okay.
Basically.
Now assume that this quadratic form is not positive definite, has a Lorentz, for instance, a signature. Is it true that it will be closed or not? I cannot imagine.
So then you want to construct Q then as with the same definition. But
the conjugation is with respect to not necessarily positive quadratic form on the vector space.
Oh, no idea how would this work out. I think that this would
be not closed.
I mean, I think that you would get problems with this intention property already, so that you might end up with elements, non-zero elements are both positive and negative. But I mean, I think that.
Well, I think if you take any, let's say, a symplectic vector space viewed as reals over reals, then you complexify it, you will immediately see that it's not necessarily closed, because on the Hermitian part, before the complexification, every vector, if you calculate the norm of V and V, the Seskey linear form, because it's symplectic, it's always 0. After the complexification, you see that every Hermitian element is 0.
But there is no norm in this case. It's pure algebra. And we are talking about A++.
But you don't require a Seskey linear form to be positive. Once dropping the positivity condition, you will immediately get some counterexample, I think. But if you add the condition that your Seskey linear form, which comes from your quadratic form,
Seskey linear form
is positive,
not positively definite.
Yeah. Then there won't be counterexamples, I think.
They won't be a counterexample. You said.
I mean, if you drop the positivity requirement,
yes,
then there will be counterexamples. One counterexample is
it would be a counterexample.
Yes, you can just complexify any symplectic vector space over the reals. And then you'll get every Hermitian element is 0, so in particular it's positive. And
so you are talking about the symplectic structure, but I'm talking about the.
And not exactly the symplectic structure. I mean, you take a symplectic structure, and then you complexify it. By complexification, I mean tensor C over the reals. And this way you get
complexify.
Okay. Yeah, exactly.
Okay.
The same complexify.
Yeah. Then you will get many interesting examples that does not verify the closedness.
Yes, I understand this. But I'm asking about a Seskey linear form, which is not positive definite.
But
you are talking about a skew symmetric form. Symplectic is skew symmetric. I'm talking about Seskey linear.
Yeah. I see your point.
And I was interested even in the case of
but after the complexification,
quadratic form of say Lorentzian signature, for instance.
Yeah. I mean, after the complexification, you still get a Seskey linear form if you define it. You define your second leg on the C as Z.
Yes, but the star is then different.
Yeah.
Star uses not only this skew symmetric part. Star uses the full Seskey linear form. Okay. And then you have these directions which are in this light cone, let's say. Okay, so I wonder, was the interaction of this light cone with this condition of being closed?
I have to say, I did not think about it. Examples that are constructed.
But there are many more examples to consider in this situation.
Basically, what happens if you
I just want to point out that it seems that all of your typical examples you are giving here are not really far from the operator algebras, right? Because C of x, C raised to the power x is just exactly the algebra of affiliated unbounded operators over L infinite of x, which is a Abelian von Neumann algebra. So all of these are not far from algebra. So do you have any examples that is
therefore I ask
seemingly very far from operator algebras?
Yeah, because these typical examples, as you rightly said.
So the typical examples are of course there because I wanted to find the stage that will in the end up there. Right?
Okay.
And then the one most non-typical example that I have that was this matrix example where you have this Hermitian non-zero nilpotent element, right? This will not. This cannot happen.
That cannot happen with operator algebras.
So what I wanted to say about this closeness condition, if you construct examples where the positive elements are just these sums of Hermitian squares, these examples, they oftentimes turn out to be non-closed. Because it's just some algebraic construction, right? And then, of course, you may ask, is there a good way to close it? Is there some closure operation? And answer is because this is not a topological closure, this is a little bit complicated, but I think I will skip this. So you can basically construct this first try of a closure, just adding all the elements that were missing. You will see that this way you get a new quadratic module, and an ordered star algebra is closed if and only if the positive elements are closed under this operation. But it turns out there are a variety of sums that I also only cite here. You find it differentiated in the.
Okay.
So this double dagger plays a role of a closure.
It is some sense. It is a sequential closure in the strongest locally convex topology. So basically, ordered star algebras, if you really want this topological point of view, ordered star algebras, closed ordered star algebras are those where the quadratic module of positive elements is sequentially closed in the strongest locally convex topology.
Okay.
That it is basically important for many applications to understand whether this is a true closure with respect to some locally convex topology. We will discuss this later, but it's complicated. And I refer to the.
So what happens to this self-adjoint nilpotence under this closure?
What happens is that you might, so in this example, you would go to the closure, you would lose this intersection property. So then the bigger, the A++ double-dagger cone, that would have a non-zero intersection with minus itself. So
So in general, this closure is not a quadratic module.
It is a quadratic module, but you might lose this intersection property.
So
But the definition of what it's
independent condition. Okay.
quadratic module and this intersection, and you might lose.
It doesn't define an order.
So basically, it means that the positive cone need not be pointed.
Yeah.
Yeah.
Yes, this is the condition that you might lose by doing this.
Yeah.
So I didn't get it.
Construction.
Positive cone need not be what? Did you say pointed?
Pointed means C intersect with minus C should be zero. This
Okay,
property
let's go
is-
pointed, okay?
Yeah.
So this doesn't define an order.
Yes, you would have in this.
It's only a pre-order. It's not
Pre-order.
an actual order. Yeah.
case you could divide out a star ideal and then you get a different star algebra, this would be ordered. But this is what happens in this example, right? Okay. So what can we do if we have a closed order star algebra? Well, then we define this map, and I will call this map a uniform norm, even though you see it goes to the closed interval from 0 to infinity, so this is not a norm in general. So it's defined as the uniform norm of A is the infimum of all lambdas in this closed interval from 0 to infinity, such that A star A is less equal than lambda squared. And for lambda being infinity, that just means, well, A star A smaller equal infinity squared, that just would always be true. And then we define the uniformly bounded part of the star algebra as those elements where this uniform norm gives a finite result. And well, what are the properties of this uniform norm? That's a very nice theorem, and I think
I'm sorry, can I ask us maybe a silly question? for the uniform norm, is it true that the uniform norm is exactly the infimum of its value under all the positive forms?
Almost, I would say, almost. I will introduce another property called sigma boundedness later, and I think for the sigma bounded closed ordered star algebras, this would be the case.
Okay, because for C-star algebras, it's the case, right?
Exactly. For C-star algebras, this would be an equivalent definition.
Yeah. Okay.
So,
in general, it may not be the equivalent definition. It's just a bounded. I mean, the square of the uniform norm is bounded by the infimum, bounded above by the infimum of the value of positive forms evaluated on A star.
yes. So basically, what could happen is that you just have not any non-zero positive form on this algebra, and then this might.
So just again, a totally stupid question. If A is not just a closed ordered star algebra in your sense, but if it is a C-star algebra, which has its canonical order, then what would this norm infinity be? Would it
be a C-star norm?
Exactly. This is what
exactly the C-star.
okay,
Yeah.
that's exactly what I thought. Yes.
That's kind of part of the theorem or corollary. So just wanted to mention, I think this is something that many people have found out, at least parts of it. I think that in all details, it was first given in a paper by Jaka Simkrich. There are parts of it that have been given by Konrad Schmidtgen, and maybe there are many other people that have found at least parts of the theorem, including me. And when I realized this, that was the point when I started to understand that ordered star algebras are important.
Sorry, I have a very basic question. Is it clear that this satisfies the triangle inequality?
Sorry, I didn't get the last.
Yes.
I have a very basic question, whether it is clear that this norm indeed satisfies the triangle inequality.
No. That's part of the theorem. And give me a second. So
I think if you use the definition playing with the epsilon, you calculate the discriminant, you will get the triangle inequality, just like one.
Yes, but you would get mixed terms. Yes.
You will get a triangle.
No, your calculator is discriminant.
But it's not obvious. Okay.
So the answer is yes, that's not obvious. So let's
Okay.
I will not give you the whole proof, but I will show you some excerpts so that you get the idea.
Yeah.
The first thing of the theorem is that for this infimum here in the equation star, there's actually a minimum. And for having elements, there's an equivalent way to describe this uniform norm by, well, the minimum of all lambda in zero infinity that bound A from below and from above. Second part is the uniformly bounded part. It's a unital star subalgebra of A, so it's again a star algebra. And in this uniformly bounded part, the uniform norm is actually a C-star norm. And if you would start with a C-star algebra, then the whole algebra itself would be its uniformly bounded part, and it would get back the C-star norm. Okay, the nice thing about the theorem is it's very, if you try to prove this is very satisfying, because there are a lot of small things that you would have to prove in here. And I think none of it is completely obvious, but everything is, in the end, when you understand it, quite easy. 2-3 lines of it. So basically the proof is elementary but non-trivial. And I would give you an example of this. So this is basically one lambda that you would need for the theorem. That's basically the equivalence of the two descriptions of the uniform norm for Hermitian elements. So for this we would need this lemma. So we want to show if we have a Hermitian element in the closed order star algebra and some lambda in 0 to infinity and minus lambda, less equal a less equal lambda is equivalent to a square less equal lambda square. How do we do this? So as a reminder, you have here the axioms of a quadratic module. So one direction, we know that lambda minus a and lambda plus a are positive. We want to show that lambda square minus a square is positive. Now, of course, we cannot just multiply the two and say product of two positive things is again positive, because this is not an axiom. What we do is first assume lambda strictly greater 0. Then we can express lambda squared minus a squared like this as the sum of the two fractions. What happens here is that in the first fraction, this is something like minus a to the 3 of lower orders. The second, the first fraction is a to the power of 3, and lower orders, and the second fraction is minus a to the third power plus lower order elements. Did you convince yourself that this identity is true?
Yeah.
So the lambda minus a times lambda gives you lambda squared minus a, and then here the plus and the minus a things they cancel, only the lambda remains, and so elementary algebra. And because lambda plus a is positive, this first fraction, which is just lambda plus a conjugated with lambda minus a, is positive, and the same goes for the second fraction, so lambda squared minus a.
The first axiom.
Yeah, you use basically the second axiom.
B star Q.
Then you use the below. Okay. And in the case lambda equals 0, then there's nothing to show because then a equals 0. Now, converse direction. So we know lambda square minus a square is positive. We have to show lambda plus and minus a are positive. Again, assume lambda strictly greater than 0. Then we can express lambda plus minus a as this way here. Again, basically the a square terms, they cancel. That's the important thing that happens here. And you see lambda square minus a square was positive for a function. Lambda and plus minus a square, that's positive because it's a square. So the whole thing is positive. That gives us lambda plus a and lambda minus a are positive. And in the case lambda equals 0, well, then this argument doesn't work. But it would work for every epsilon strictly greater than 0. So we already know epsilon plus a and epsilon minus a are positive. Because this is true for all epsilon strictly greater than 0, we get by a closeness property that plus and minus a are. Okay, so this is where closeness comes in. And basically, this is also what shows that we do not have in those ordered star algebras, we do not have nilpotent elements, nilpotent emission elements. So here's the theorem back again. What are the corollaries? No non-trivial nilpotent emission elements in closed ordered star algebras. It's funny that we get this from this algebraic property from an analytic property, this closeness. Now, if we call an ordered star algebra uniformly bounded, for insights with its uniformly bounded part, then we see that the uniformly bounded closed ordered star algebras are precisely the pre-C star algebras. In this case, we get so if we start with a uniformly bounded closed ordered star algebra, then we get a C star norm that turns it into a pre-C star algebra. For pre-C star algebras, we have this unique ordering on the C star completion, which well, that's the way how we go back. And this, to me, this means an order on a star algebra is more powerful than a C star norm. So basically, an order on a star algebra that makes sense also in the unbounded case. In the bounded case, we get back a C star norm. So then basically in the bounded case, both approaches to describe the essentially same object are equivalent, but the order also makes sense in the unbounded setting. Now, if we consider morphisms between star algebras, there's a natural notion of the morphisms between ordered star algebras. you need a positive unital star homomorphisms. So unital star homomorphism is self-explanatory. That's the unit, compatible with the star, additive, multiplicative. It's called positive if it maps positive elements to positive elements. Now, if we have uniformly bounded and closed ordered star algebras, and if we have a positive, well, then a positive unital star homomorphism between them is equivalent to a norm-continuous morphism. So that the positivity gives us norm continuity that is kind of clear because we constructed a norm out of the order. So compatibility with the order giving us compatibility with the norm makes sense. The other way around, you need some C-star algebra technology. Continuous unital star homomorphism extends to the C-star completion. And because we have a unique, because the order on a C-star completion is uniquely determined, we find that the positivity is then automatic. Essentially because you have square roots in a C-star algebra.
Can you explain this statement? An order on a star algebra is a more powerful concept than a C-star norm?
So it is, let's say, so basically what this theorem shows us is that the category of pre-C-star algebras arises as a subcategory of the category of ordered star algebras.
Okay.
So this way, if we discuss ordered star algebras, we can, in this language of ordered star algebras, we can efficiently talk about pre-C-star algebras, which are just one special case of ordered star algebras. And but so these two notions are not only equivalent in this bounded case, because the ordering also makes sense for unbounded star algebras, where the C-star norm just.
Okay, so yeah. So I've got you. So the point is that when you say more powerful, you mean like more general, it has a broader scope, and
in this case, powerful is not a.
It covers more cases, I think. That's what you mean.
This is why this question is. I wanted to know in what sense you mean. Okay, I've got you.
And most important, that some properties of pre-C-star algebras can be deduced in this more general setting only via this positive condition.
Yes.
Yeah, like absence of self-adjoint nilpotence, for instance.
For example. And so
completeness with respect to the norm is irrelevant.
So maybe some of you, once in a while, they give lectures on C-star algebra. Right?
Yes, I get it.
So basically, this means that there are two possibilities how to approach this lecture. You could use the ordered star algebra definition or the classical one. And I would say it just depends on what you would like to focus on, which approach would be easier. So if you start with the classical one, you are basically forced to go through the Banach star algebra theory in order to go to spectral theorems or something like this. With the ordered star algebra approach, well, it's just a different approach, and the way how you build up your theory would just be different and maybe more applicable if you depending on what topics you would like to cover, or what is your end goal.
So in the previous example, if you remove unital condition.
Sorry?
So you have taken unital star homomorphism, right?
Yes.
So if you remove unital condition, then what can you say about the implications?
Oh, I really don't like to think about a non-unital case. I think in a non-unital case, all of this is just
No, so A and
finite. So you would have to cook up.
no, A and B, everything are unital, but just P does not preserve one. So P, the map is not unital. A and B, everything is unital.
So you still want unital algebras, but phi which is not unital.
For example, in C-star algebra case, it is always positive, even if you consider non-unital.
But then it reduces the unital case, right? You just consider the subalgebra of B generated by the image of phi. It would be a unital one.
No, algebras are unital. I am not saying algebras are not unital. The map is not.
I understand, but you consider the subalgebra, not necessarily unital, the subalgebra generated by the image of phi, and then phi 1 would be the unit of
Yeah,
the subalgebra.
yes,
It reduces to the unital
Yes.
mapping case.
yes, you're right.
But this means you have to. Yeah, okay.
So yeah, back in the unital case somehow, yeah.
Original unit,
Yeah.
but then
Yeah, because phi 1 would be.
Because you already require your map to preserve the order, so it's exactly back to the unital mapping case.
Yeah, okay.
So it's, I think, positive non-unital star homomorphism giving you something non-continuous. That would certainly be true. The other way around, I'm just not sure how this would play out. Maybe then can't go back. It's like it. Sorry, not sure. Maybe discuss this later. Okay, I think I will have to skip this here. So I wanted to show that from this ordered star algebra approach, it's actually quite easy to build up the continuous calculus of C-star algebras. The basic idea is what you need to do is you need to be able to describe the polynomials that are pointwise positive on an interval. And this is actually, I mean, this is just applying the fundamental theorem of algebra and looking at the roots, and you find that these pointwise positive elements can be described like this, and then basically, but I think I don't have the time to explain the details. And basically, you can extend the polynomial calculus by positivity of the polynomial calculus, which you get from this description of the pointwise positive elements. You can extend the polynomial calculus to the continuous calculus because positivity implies continuity. Okay, but no time for this. What this means is, so this description of the pointwise positive elements is called a Positivstellensatz. This would be one of the easiest Positivstellensätze that exists.
Can we, just one question, can we understand this by using your previous description that the closed ordered star algebras are exactly, well, for such algebras, the positive cone are closed under the strongest locally convex topology, and then you just
yes,
do the continuous functional calculus along every linear form, and you can take the closure because it's the sequential closure of the polynomial combinations.
this certainly is a way how you could understand it. I will actually come back to this now more general.
I think you can you extract an actual proof from this idea? I don't know. It seems plausible.
Yeah, well, yes, I think you can, because but this would, I think
Okay,
this
okay.
would go over representation theorem, so it would certainly be more complicated
Okay.
than this one, but I think it would work.
Okay, thank you.
Okay.
Sorry, so everything is about positive functional calculus. So you said that your approach is better than C-star algebraic approach, but C-star algebraic approach allows us to construct functional calculus, for instance, for normal operators.
If you want to do this, then you would need a little bit more general Positivstellensatz to start,
Okay, good.
which then gets a little bit more complicated.
So this is a positive functional calculus.
And let's say I don't want to claim that this approach is better. I just would like to claim, depending on, this is an alternative approach, and well, depending on what you in the end want to do, one might be shorter or
Okay.
Now enter the Archimedes.
Unfortunately, I have to hurry up. So the whole point is that the closeness condition and the uniformly boundedness conditions are called being Archimedean, both in the different communities of mathematicians. That's unfortunate, and that's in order to annoy both communities equally, I chose to not use Archimedean here. Okay, but So we should start to come closer to the big theorems. So what are star representations? We have the two standard models, standard examples of ordered star algebras. So we define a star representation by operators of an ordered star algebra. It is a tuple of a Hilbert space and a positive unit star homomorphism from the star algebra to the adjointable operators on this Hilbert space. And our representation is more faithful if this representation that is an isomorphism of the image. And here isomorphism is in the algebraic, is understood in the algebraic sense and in the order theoretic sense. So mapping positive elements to positive elements, and the pre-image of a positive element also should be positive. Okay. So the strongest sense of would think of isomorphism in this setting. And of course, if A is closed and uniformly bounded, then it is a algebra, then the Gelfand-Naimark theorems apply. And so in this case, we get a faithful star representation by operators. And the other type of star representation that's interesting is the star representation by functions. That's a tuple of a set X and a representation like pi, which is a positive unit star homomorphism from A to the ordered star algebra of functions on X. And again, it's called faithful if it's an isomorphism with the image.
So then A must be commutative.
In this case, A must be commutative. So for non-commutative star algebra, you certainly can find star representation by functions. And again, Naimark tells us if we're close to uniformly bounded and commutative ordered star algebra, then we get a full star representation by functions. Okay, the point of this talk is to show that these theorems can be generalized to a larger class of ordered star algebras, namely the sigma-bounded ones. So I want to replace the uniformly boundedness condition by this weaker sigma-boundedness condition. An ordered star algebra is sigma-bounded if there exists an increasing sequence of positive elements that is cofinal. So that means for every Hermitian element B, there's some element A hat n in the sequence that dominates the P. So for example, every pre-C star algebra is sigma-bounded. In this case, we can take, well, the natural numbers as this increasing sequence. But one other important example are the counterfeit generated ordered star algebras, because they have a countable dimension as a vector space. Then we can just choose a vector space basis B1 and so on of the Hermitian elements, and we can use that every B is plus or minus B is dominated by 1 plus B squared half. I mean, that's basically you move the B to the right hand side, and then you see that this is a square on the right hand side, so it's positive. And then if we kind of add all these 1 plus B squared halves up in this way and multiply with n, we get a sequence that will eventually will dominate every of the basis vectors, and then also every linear combination of them. So basically, sigma-bounded ordered star algebras or sigma-bounded closed ordered star algebras, they contain increasing star algebras, but also more examples, especially these other examples would be unbounded. Oh. Oops. Okay, first big theorem. Well, not the first big theorem, but the first big theorem. If we have a sigma-bounded closed ordered star algebra, then A has a faithful star representation by operators. Okay, I want to give you at least a short summary of it. How can we construct star representations? That's the usual tool, the GMS construction. This is completely algebraic. This also works for ordered star algebras. So if we have a positive linear functional, so mapping Hermitian elements to the reals, mapping positive elements to the positive numbers. Then we can use this to construct a pre-Hilbert space out of the star algebra by considering the quotient of A over this whole set. And by some Cauchy-Schwarz inequality argument, you find that the set that I want to divide out is actually a linear subspace. The inner product can be constructed out of the positive functional. And the representation, well, is basically by left multiplication with which descends to the quotient. So that's the TNS construction as usual, and this gives us for ordered star algebras, it gives us a star representation of operators. So what we have to show is that there exist many positive linear functionals. And more precisely, for every non-positive Hermitian element, we need to find a positive linear functional that shows that this element was not positive. How do we do this? We want to construct certain functionals. The way to do this is IMPAN theorem. More precisely, well, if the cone of positive elements would actually be closed in a locally convex topology, then for every element that's not in this cone, we would get a continuous linear functional that separates this element from the convex cone by IMPAN theorem. And it turns out this linear functional is positive, and it gives a negative result on this element that you wanted to separate from the cone. So what we have to do is show that the cone of positive elements is closed in a locally convex topology. How can we construct this locally convex topology? This is where we use the sigma boundaries. So we have this cofinite sequence in the positive element, and for any sequence of positive real numbers, strictly positive real numbers, we can define this set U delta as this kind of union of order intervals. So an order interval is just defined like a usual interval in R, but in a partially ordered space. So all the elements that are between the lower bound and the upper bound. And with this definition, the important thing is that what we get here is an absorbing set. So instead, a set, if we multiply it with arbitrarily large real numbers, it will cover the whole space. The reason why this is absorbing is because this sequence A hat was cofinal. So for any element, any Hermitian element, there will be an A hat n that is larger than this element. And so if we multiply with the corresponding coefficient, if you multiply the U delta with the corresponding coefficient, this element would be U delta. And that these sets U delta are balanced and convex, that's already the order intervals are balanced and convex. So what this means is we get a zero neighborhood like this. And actually one can show for every non-positive element, there is such a absorbing balanced convex set U delta that separates this non-positive element from the cone of positive function, from the cone of positive elements. And at this point, one needs to use the closeness property of A.
The typo in convex.
Convex, yes.
Oh, there is a typo. Well, finally.
Aha. 1-0 for the audience.
So actually, I think all the parts of this theorem, they have already appeared somewhere. So there's a book of Konrad Lütgen about star algebras of operators and the representation theorem, and there these zero neighborhoods, they occur. Just and I think the topology, he discusses the topology that occurs that you construct like this, but somehow I couldn't find one reference where all these points are put together.
Yeah.
Because I think that it's a very nice result.
Yeah.
Maybe it should be well known. It should be better known.
So all this mimics the proof of GNS construction.
Yes.
With this modification that this confinedness gives you this absorbing balance and convex substance.
Yes.
So this part is easier for sister algebras. So we have a replacement for this.
And for C-star algebras, you could argue mostly the same, but your locally convex topology would just be C-star topology. Okay. That's the first of the Gelfand-Naimark theorems. The representation by functions, that's a little bit trickier. Because, well, there is a very similar argument, but we do not need just positive unital, do not need positive linear functionals, we need positive unital star homomorphisms, which, well, is just as stronger. Well, we have to construct functionals that fulfill stronger algebraic conditions. If we can do this, well, the usual Gelfand transformation will give us by functions. Okay, so for the Gelfand-Naimark theorem in the commutative case, we need to construct positive unital star homomorphisms from A to C. How can we do this? So, usual definition, what is a state on an ordered star algebra? It's a positive linear functional which fulfills this normalization condition. And this, okay, this is not the usual definition of a state, because here positivity is understood with respect to the ordering star algebra, not with respect to the standard code of sums of Hermitian space. And if we have a state, then we can define its variance like this, basically motivated from the usual definition of a variance of a probability measure. And it turns out I really have to hurry up a little bit. Using the variance, you can prove this nice inequality, and you find, here's the proof, I don't have that time for it. You find a positive unital star homomorphism on an ordered star algebra is equivalent to a state that has zero variance. Or is it variance?
I think it's variance.
It's variance. I'm sorry.
So it's a counterpart of multiplicative, say, character, something like this.
Yes, well, you could say positive unital star homomorphism maybe as a replacement, but this is just a positive star character.
But this is still true in the sister algebra case.
Yes, so ordered star algebras especially contain the C star algebras. So this characterization by vanishing variance, that's true in the C star algebra. And from this, it follows that every positive unital star homomorphism on an ordered star algebra is an extreme point of the convex set of states, meaning not a non-trivial convex combination of other states. That follows from this variance characterization, because the variance is essentially concave, strictly concave. Question is the converse true? That's the problem. Okay, and the answer is no, this would be way too easy. But if this were true, then this would be great, because there are actually many extremal states on the sigma-bounded closed ordered star algebras. I don't give you the proof here. You use just standard theorems, Banach-Alaoglu and Klein-Millman. Now, the important thing to remember here is the state space of an ordered star algebra is not necessarily compact. So we cannot apply Klein-Millman to the space of all the states. But one can still apply Klein-Millman to the polar of these zero neighborhoods from the proof before, intersected with the positive functionals. And this, because the polar of the zero neighborhood is something compact, we can apply Klein-Millman to it. And then it turns out that the extreme points of this polar set, they are not extremal states, but they can be rescaled to extremal states. That uses some, that is not true in general, that uses some special properties of this zero neighborhood from the previous and prove that maybe just a coincidence it works so well.
So sorry, essentially you are saying that it is not true that if you have a pure state, then this is indeed a star homomorphism, yes, which is okay, which is well-known fact in the context of a C-star algebras already.
No, well,
am I right?
No, so in a C-star algebra, every extremal state is a star character, is a unital star homomorphism.
No, in the context of commutative, but not in general.
Commutative.
But it's why I'm talking commutative, right?
Yeah.
Yes. I mean, here I mean, for this corollary, I don't need a commutative adjective, but it's only interesting in the commutative case. And also,
okay, so this is a general assumption, yes. In this case, okay.
So the representation
About functional representation of the C-star algebra. It's in terms of functional representation of C-star algebra still. You are continuing this.
No.
Okay.
Oh. What is this about?
I am a little bit confused. Can we actually find some state in this form that is extremal on closed ordered star algebras that is abelian, but it's not a character?
the next slide is for you. I'm really running out of time, but this example is really important. So we consider polynomial star algebra in two variables, x and y, two Hermitian variables. Then we can turn this into an ordered star algebra by setting the positive elements to be just the sums of Hermitian squares. Because the sums of Hermitian squares, they are necessarily pointwise positive. This means it is the detection property equal. So we really get a closed ordered star algebra like this. Oh, we get an ordered star algebra like this. And this is closed. You need some analysis to do this. And this is also sigma bounded because it's a finitely generated star algebra. However, it's well known that there are polynomials in two variables, which are sums of Hermitian squares, which are pointwise positive on whole R2, but which are not sums of Hermitian squares. This here is an example of it. So it's, well, elementary analysis rejected this is really strictly positive on whole R2. It is not a sum of Hermitian squares. Basically, you make an ansatz. The elements in your ansatz, their degree is bounded from above because you cannot cancel the highest degree elements. And then you see no way to get this as a sum of Hermitian squares. What does this mean? This means that this ordering is not the usual pointwise one. But the polynomial star algebra with this sum of Hermitian squares ordering, it still has a faithful star representation. It still has a faithful star representation by operators by the previous theorem. But it does not have a faithful star representation by functions. Because in such a faithful star representation, this polynomial P could not be pointwise positive because it is not positive with respect to this strange ordering.
Sorry, there's a silly question. When you say a faithful star representation by operators, you mean not necessarily bounded. Unbounded is fine as well.
Unbounded is fine. So, okay, there's a big history to this. Like Weierstrass in his PhD defense convinced Hilbert that such polynomials exist, and Hilbert proved it abstractly. And for some reason, the first explicit example is Motzkin's polynomial, which is similar to this one, and which was given like 50 years later after it was general proof. The point is.
For polynomials in a single variable,
Sorry?
in the case of polynomials in a single variable, such a counterexample is not possible.
No. In the case of a single variable, every pointwise positive polynomial on the real line is a square,
Okay.
by fundamental theorem of algebra, essentially. So I need to go to the two variable case here. And because this algebra is sigma bounded, it's a closed ordered sigma bounded star algebra. The Klein-Millman argument that I didn't show you shows that there are actually extremal states that are not multiplicative on this star algebra with this weird ordering. Okay. One last observation. No time, check for yourself. If you multiply this p by 1 plus x squared plus y squared, you get something, which is a sum of Hermitian squares. And this is strange. I mean, if you want to represent this by functions, if you have a function, which if you multiply it with an obviously positive function, and you get something that's positive, the original function was positive, right? But this does not translate in this abstract sense. So this pathological example is the one that we have to exclude in order to get a faithful star representation by functions. So here's the important definition. Say a commutative ordered star algebra is radical. If this is true, if we have a positive element A and some Hermitian element B, and 1 plus A times B is positive, then we want that B already was positive. This is something for ordered star algebras of functions, this is clearly true. But as the previous example showed, this is not true in general for arbitrary commutative ordered star algebras.
Why do you want to exclude this case? You could localize with respect to the system of strictly positive elements, and then you will obtain functions which are fractions whose denominators are non-zero everywhere. Okay?
Yeah.
So what's wrong with this representation?
Well, there's nothing wrong with it. This is exactly what I want to have.
So, okay.
Basically, the theorem is, the theorem comes here. If we have a commutative, ordered star algebra and a state on it, and if this commutative ordered star algebra is radical in this sense, then omega is multiplicative if and only if it is extremal. So this condition, that's what I think calling this thing radical is just not a good idea.
I agree.
Sorry. If you give me any other name for it, I will take it.
Yeah, and of course, in sister algebras, such 1 plus A is invertible, so you can have it as well, right? That B must be positive.
Yeah. The sister algebra case is automatically fulfilled. This is why, well, it's a sister algebra case. Okay. And now it's running out of time. From this it follows, if we have a radical commutative sigma bounded closed ordered star algebras, okay, a lot of adjectives here, then this has a faithful star representation as functions. So basically, and the proof now is more or less what we've discussed so far. We need many positive unit star homomorphisms. We already know we have many extremal states. Because of the commutative and radical assumptions, these extremal states are multiplicative and we get our faithful star representation. Okay, time's up. I think I'm mostly through. let's discuss the necessity of the assumptions, because the star algebras of operators and functions, they are closed. We need a closeness assumption in the theorems. The sigma boundedness can in general not be dropped. Something like, if you consider rational functions, they do not, they look a lot like a star algebra of functions, but they are not. And it turns out they would be commutative, radical, sigma bounded, closed, but they do not have, they are not sigma bounded. They are commutative, radical, closed. But they do not have a faithful star representation as functions.
And we say a faithful star representation as functions, these are functions on what? What's the space?
Arbitrary set.
Arbitrary set.
Wait a moment.
I mean,
But the rational functions whose denominators are everywhere non-zero.
Yes.
These are functions which are
the star algebra of all rational functions is not a star algebra of functions. Not of complex. It's not a star algebra of complex functions because they are not functions. They are not complex valued functions on the whole real line. You would have to exclude the poles, but poles are just everywhere.
But no, poles are outside this set. You are talking yes, I understand. So you are considering always points as multiplicative functionals. Okay. And they correspond to the ideals in the complexification in a sense. It's a complex algebra.
Yes, I mean, it can take a very complex star algebra.
Yeah.
So maybe if you look at this example, it already looks like this shows sigma boundedness cannot be dropped, but without sigma boundedness, this counter example, it looks a lot like star algebra of functions, just it is not really. So it almost seems like pedantry to say that this is not a star algebra of functions. And so maybe I think one can probably drop the sigma boundedness if one, if one is willing to talk about the star algebras of functions which may be only then defined on a dense subset of some topological space, but not a theorem yet. Important thing is all the counterfeit generated usual stars of algebras are sigma bounded, so this sigma boundedness is not really a restriction. It applies essentially everywhere if you are willing to restrict to a nice.
So rational functions are not countably generated. You can have denominators, continuous family of denominators.
Yes. So in the end, well, the radical and commutative assumptions, so of course we need this in the commutative case for the star representation of functions because that's what functions are. Okay, basically I'm finished. The rest is just philosophical remarks. It is a little bit strange that for the commutative representation theorem, we need the assumptions of the non-commutative ones plus commutativity plus one additional condition. And this means that star algebras of operators, they are not just a non-commutative analog of star algebras of functions in the unbounded sense, because they lack some additional condition that just occurs in a commutative case without any clear way how to extend it to a non-commutative setting. So the question is there a good non-commutative generalization of this radical property, which maybe gives some important, nice notion of non-commutative ordered star algebras. And this is, I think, important for quantum theory because now look at it like this. You say a quantum theory is described by a star algebra of operators, maybe an unbounded one. If you think of it in the sense of deformation quantization, you have such an observable algebra for every strictly greater than 0 h bar. And you say in the limit h bar going to 0, you get a commutative star algebra, which you would like to represent as a star algebra of functions. Because we know classical physics is described by an observable algebra, which is a star algebra of functions. But it is unbounded since it is completely unclear why this classical limit should have this radical property. The obvious idea here is, I think, that the quantum theory already, well, it's not just described by any ordered star algebra, not by any star algebra operators, but by one that fulfills some non-commutative generalization of this radicalness. And I have ideas about this, but that's for a different day.
Okay, so
Okay.
thank you very much.
Just for the record. I
Reference.
had some references in the talks. Here you have them.
You were in bluff. Okay, great. So if there are any further questions, let's ask them. Anybody in the room?
I have a question. Maybe not a question, a comment. So first about this radical. If you have a faithful representation of an algebra into some radical algebra, then the kernel must be 0. So this means that this faithful representation kills the radical in the classical sense. So you are demanding that elements which multiplied by strictly positive or with some, I don't know, in sister algebras it would be the condition of the spectrum bounded from 0. Okay, is this an idea?
So you mean whether you can divide out a star idea so that the
Yes, which are killed by
have this radicalness property.
It is an ideal. It is a good counterpart of a radical, but if not, then I don't know.
So I think you can construct such a. I think you can construct a star ideal that you have to divide out. Now, it really was not a good idea to call this radical. So the idea why I call this radical is there's this notion of radical ideals,
Yes.
which are the vanishing ideals of a set in a complex polynomial algebra. And these radical orderings, they are basically the orderings that are the positive, that are the quadratic module of pointwise positive elements in a star algebra of functions. So this is the idea that I had in mind, but I think it's confusing.
So this is related to the operation of localization or inverting conforming fractions with strictly positive denominators.
Yeah.
Okay. And then
In some sense, the nice property that one needs is that the positive elements behave as if certain elements would be invertible. Right? I mean, this 1 plus 8 is not necessarily invertible in my algebra, but I want to be able to divide it out.
Yeah.
So at least on the level of the positive elements, these positive elements must carry some resemblance of the possibility to maybe divide out this 1 plus 8.
okay. So are you sure that your theory cannot be how to say enhanced to be extended to this case of rational functions, which are not functions in your theory? Because rational functions are, of course, they are functions, okay? If your theory makes rational functions not to be functions, It's an argument against your theorem.
Well, it's pedantry, because they are not complex, they are not a star algebra of complex valued functions by the definition of.
Now, you are considering these poles laying outside this classical domain of this function. So it's like complex algebra in algebraic geometry when you allow irrational roots. So complex solutions to the system of polynomial equations. You are taking this into consideration. But in the classical case, oh, by the way, do you have in your theory anything of type of Stone-Weierstrass theorem?
Yeah, I mean, you can generalize the Stone.
So you have complex functions on an interval. You can approximate functions on an interval by polynomials, okay? But if you instead of taking this interval, you are taking wider and wider intervals tending to the line, okay? You are losing this property of approximation, but then you can speak about rational functions which do not have zeros of denominators on this real line. Why, in your theory, you are taking into consideration, taking into account these complex roots of these polynomials? How they appear?
No, where do I?
If you have a positive denominator, these functions everywhere defined. So it's a very good continuous function.
Yeah. So I mean, if you take the star algebra of rational functions whose denominator is strictly positive,
yes,
this would still be a sigma-bounded closed radical commutative ordered star algebra. To this, the theorem would apply.
Yeah. Okay, but why there is no dysfunctional representation of such things?
Well, it is. In this,
So I missed something.
In this case, so if you just consider rational functions that have no poles on the real line, then the theorem applies.
Yes.
The case where it does not apply is the star algebra of all the rational functions.
Yes, but when I was talking about inverting elements of one plus positive element, I was talking about denominators that are everywhere positive.
Yeah.
So such fractions do not admit, they do admit functional representation.
Yes.
I had the impression that you said no.
No, but we just clarified that he
Now,
yes.
now it's clear for me. But before I had the impression that there is something wrong with such fractions.
No.
Okay, good.
I think it really was a mistake to
My bad. Okay.
call this thing radical, because this is not something I want to divide out. So there is no radical that I want to divide out. This radical, this adjective, is a property of a quadratic module of the ordered star algebra that I want to have. Okay, I think I see that this was not, that I did not baptize this property with much
Okay, anybody on Zoom would like to weigh in? Adam, Hua, George?
No, I'm happy.
Hua, are you happy?
Actually, I have a conjecture. I don't know if it makes sense or okay. Suppose I'm taking, let's say, an arbitrary compact space. It's a bare space in the sense that itself is of second category, and every open set is of second category. Now I consider the algebra of Borel measurable functions on this compact space. Let's call it X. And my order is as follows. I call F positive if f takes positive values outside a set of first category. Okay, so now it's a closed star ordered algebra, which is abelian. And my question is, can any closed star ordered algebra, which is abelian, arise as a subalgebra of this one? So it's a more general representation theorem.
So you need the radical property?
No, I don't think this guy is radical. No. It's slightly more sophisticated.
Oh, I'm sorry, but so I think this is precisely the way how one could construct.
Because, for example, your second example arises as a subalgebra of this one. Well, you can replace X with any space. Let's say R2 is a bare, C2 is a bare space, right? And your rational functions are just just measurable functions that well, the zeros are meager.
Yes.
Yeah, so it's really a subalgebra of this one, of this sort of example. So you can, such examples in general are not radical, but my question is, using these algebras as models, can you represent faithfully any commutative star closed algebras?
Well, again, I think you have to add this radical property.
I mean,
because
if you consider, let's say,
representation means also with respect to the order, and the star algebra that you gave, this is radical. I mean,
no, the algebra I just constructed cannot be radical. For example, you can consider your last example of rational functions in two variables, right? And I view C2 as a topological space. It's a bare space.
Yes.
Yes. And I consider all the Borel measurable functions on C2.
Yes.
And my order is if the function is positive if and only if outside a set of first category, it takes positive values. So your algebra of rational functions really did appear as an ordered subalgebra of my construction.
Yes.
But yeah.
Wait a second. Can we go backwards? This.
Yes.
Here. So you are talking. No, this one. What is this?
I was trying to represent all the commutative closed star ordered algebras.
So you were just talking about this example, right?
Yeah, exactly.
No.
No, not exactly. I think it's about the end of the talk. Yeah.
Okay.
When you introduce the radical property, you consider the rational functions in two variables.
I think there's just some confusion about the definitions here. So just let's go through it.
Yeah.
This was the definition of a radical commutative ordered star algebra.
Yeah, exactly.
The example that you just gave of measurable functions, this fulfills this radical property. Because if you have some real valued measurable functions and you multiply it with one plus a positive valued measurable function, and if you then get something which is positive in your way, pointwise positive except for a category 1 set, then your original function was already pointwise positive except for this set. Okay? So the example that you gave, this is radical.
The thing is, using this sort of examples, your algebra of rational functions in two variables did appear as a subalgebra.
As a
You can just show the following, maybe.
so
If I remember correctly, you're saying that your algebra of
pressing the
rational
wrong buttons.
functions. You're saying your algebra of rational functions in two variables is not radical, which is why you cannot represent them,
wait,
right?
sorry, I think
Maybe I misunderstood.
I think I did not talk about rational functions in two variables.
Okay.
So the not radical function, the not radical example was this polynomial functions in two variables,
Okay.
and the rational functions. That's here the not sigma bounded.
But
example.
so far I didn't see any example that is abelian that cannot arise as a subalgebra of the construction I just gave.
Well,
So
this
it's plausible to, yeah.
I mean, it's one. The point is, faithful representation for me also means taking in account the order. So
yeah, exactly.
So basically, this example here, this also will not appear well as a subalgebra with the relative order of these measurable functions.
Yeah,
And
but
this
it's
was non-radical example. Okay.
Okay.
So I think what you said, this is really the way to generalize this representation theorem, but it allows us to drop the sigma boundedness assumption.
Yeah, exactly.
It does not allow us to drop the radical.
Ah, okay, I see.
Okay.
Okay,
And actually, there is an old theorem that does exactly this, but not for ordered star algebras, but for a certain type of lattice ordered star algebras. It's really old, 50s, something like that. Maybe we can also put I can also put the reference then in the comments of the YouTube video.
But yeah, surely, yes. On YouTube, yes.
So and I guess this theorem could maybe really be extended to the, well, not necessarily lattice ordered algebras. And then we would be, so basically then we would get a theorem like, then we would get that A be a radical, commutative, closed ordered star algebra, then A has a faithful star representation as, well, functions which are almost everywhere well defined, something like this.
Okay, thank you.
Hey, I have a very simple-minded question. I'm sorry for being so naive. Do your Gelfand-Naimark theorems, so this is this commutative one, and earlier we have this operator algebraic one, do they imply, in a strict logical sense, the usual Gelfand-Naimark, like the generalized Gelfand-Naimark, and they imply, right?
Yes.
Okay.
So basically, commutative is clear. Sigma bounded is just stronger than uniformly bounded, which was the C-star algebraic case. And this radicalness condition, this is something you can prove in a C-star algebraic case. That's, because you can invert the strictly positive elements essentially.
So I have one more speculative, one question to speculative, again naive. I'm obsessed with graph sister algebras. And when you have graphs, you have very natural orders. Orders come hand in hand with graphs because you can order by paths, and paths give you elements in a sister algebra. So I'm wondering if you take this usual order which you have in a sister algebra, okay, because you have this canonical order, you talked about it, I'm wondering how it is related to the natural order for graphs that you have. So imagine you have a graph sister algebra for a given graph, and you have some, for instance, you say that alpha precedes beta, alpha is a path, beta is a path. If beta extends the path alpha to the right, this is very important order that you use in graph sister algebras. And then it somehow also gives you order between sister elements of your graph sister algebra associated to paths. And I'm just occurred to me a completely naive, silly question. Does it agree with the order you have from your?
How does this give you an ordering on the C-star algebra?
I'm not claiming this. It gives you an order on paths, but paths are been represented but not faithfully as elements of your sister algebra by multiplying partial isometries out.
But this is an order on generators.
Yeah,
Not on the
yeah. I'm not saying it is. I'm not saying it is, but somehow. Okay, I have an order on the space of paths, or maybe it's not the full order. It's stuff like this. I mean, it's partial order, and then this, but to every path you associate with an element in your sister algebra.
Yeah.
So now I'm wondering if alpha precedes beta in this pre-order of passes. It's true that my sister element S alpha precedes the element S beta in the sense of the canonical order on a sister algebra.
But this, I mean, the elements of the different orderized as partial isometries, which are not necessarily Hermitian, right?
No, of course not.
And this ordering.
So it's completely orthogonal concept. Yes. Okay. Just sure. Okay. Okay. That's a good argument. Yes. They are of course partialism, so they are not Hermitian. Yes. Okay. These orders are irrelevant. Okay.
I think the condition that X is positive implies the elements of the form AX, A star is positive is really strong. So it should imply that the order induced from your graph is very close, if not identical to the Euro order on the graph C star algebra. Yeah.
Okay, but we can.
So may I suggest something? Let me continue for a while. This problem with these rational functions, which turn out not to be a problem, okay? But I see some possibility here. If instead of taking this A++ H, which is a subset of the algebra itself, you consider subset of fractions with nominators coming from your A++, but denominators being strictly positive elements or elements of the form 1 plus some positive thing, then I think this interpretation of this functional representation of a commutative would be simpler in a sense.
Yes, so basically with this, so
for the price of this order being defined not on the level of algebra itself, but on the level of fractions which such denominators I described.
I think this would, in the end, this would mean that the order is so. If you pull the order back to your original algebra, this would mean that this order that you get like this would necessarily be radical, because it came from this larger algebra
Yes.
that would divide out things.
Yeah, but
So,
no.
If you formulate the theorem for this only for this larger algebra, then I think then you don't need this radical property, because it would kind of be automatic because you can divide out.
Yeah, and then the representation would be the representation of this algebra of fractions, not the algebra itself, which is too small.
Yes.
Okay.
And this is actually, this is really also maybe one possibility what a good non-commutative generalization is.
Mhm.
So the non-commutative case, it seems like you also need to talk about star algebras in which certain elements are invertible. That makes
You mean some affiliated elements? Multipliers? What kind of?
well, just a strictly positive. For example, if you consider the Weil algebra, and you extend the Weil algebra, so the Weil algebra in the sense of the star algebra that's generated by two elements, two emission elements P and Q, with the PQ minus QP equals I relation. Now, if you extend the star algebra to a larger star algebra where the P square plus Q square is invertible. This larger star algebra has much nicer properties. For example, all its irreducible star representations are just the Schrödinger representation or unitarily equivalent to it. And this is, I think, the non-commutative analog of, well, what you just said, if we consider commutative star algebras which have a lot of invertible elements, then we automatically get this functional representation theorem. Okay. Yeah, there's a lot of, I think are still a lot of interesting theorems out there.
Okay, on this positive note, let us thank Andreas. Matthias. Sorry, I looked at Andreas. This is why I said Andreas. Matthias, of course. So let me stop the recording. Thank you guys for being here. Just first, I need to stop share, and now I go and stop.
Fyodor,